Welcome to the online lecture series of Heat and Mass Transfer. Here is Professor Lakshman Mane. This is a video session on one-dimensional steady-state heat conduction without internal heat generation. In this session, you will be able to explain steady-state heat conduction without heat generation for plain slab or wall, hollow cylinder and hollow sphere. Steady-state heat conduction without internal heat generation. General heat conduction, three-dimensional differential equation in Cartesian coordinates, that is, we have seen in last video, del square t by del x square plus del square t by del y square plus del square t by del z square plus q upon k is equal to 1 upon alpha into del t by del t. So in this case, these are the second order differential terms along x, y, z direction, that is Cartesian coordinates. This is internal heat generation and this is the thermal diffusivity, that is alpha. Now in this case, if we write this equation in this way, then here delta square will be called as Laplace operator. Now we have seen also different forms of differential equation for heat conduction. When there is no heat generation, means Qg is equal to 0 and unsteady state, then the equation form becomes, that is called as Fourier equation. In case of steady state heat conduction, means this term is 0. In that case, this form of equation which is reduced, that is called as Poisson equation, and steady state and with no heat generation, the form of the equation is reduced to this, that is called as Laplace equation. When we consider only one direction, means along x direction, then the equation for steady state with internal heat generation, we get this. This is known as one directional Poisson's equation. Now, why we consider one dimensional heat flow, that is applications of Laplace equation? Because solution of simplified version of heat conduction equation for cases of simple geometries gives result with acceptable accuracy for engineering applications such as boiler furnace wall, where heat transfer take place across wall to the surrounding from furnace inside. In case of pipe carrying steam from boiler, heat transfer take place along radial direction to the surrounding from the pipe center. In case of spherical shell, which is used to store chemical gases, here heat transfer take place along radial direction to the surrounding. So, as a large slab or wall, as per shown here, that is a furnace wall, here length in one direction, say thickness, is small as compared to other two dimensions, means width and height. In this case, temperature varies along its thickness, that is L. In case of steam pipe, means long cylinder which is hollow, where heat is passing from inside to outside. So temperature is assumed to be vary only along its radius. In case of spherical shell, where temperature is assumed to be vary only along its radius. So now we will see steady state, one directional heat flow through an infinite slab without internal heat generation. So here in this diagram you can see infinite having thermal conductivity K. This is infinitesimal element of the wall, while surfaces are maintained at temperature T1 and T2. T1 is the left side temperature, T2 is right side temperature. In this case, temperature becomes function of x direction, means one direction only, and rate of heat generation is 0, as the steady state condition means there is no change in temperature with respect to time. So delta T by delta T is equal to 0. So the differential equation in Cartesian coordinates reduces to this form, that is Laplace form del square T by del x square is equal to 0. Now we have to get the equation for slab. So what we have to do? We have to integrate this equation, which is differential form. So integrating with respect to x, we get dt by dx is equal to C1, means constant of integration. We say this equation as equation number 1. Integrating above equation, once again with respect to x, we get left side integration of dt by dx with respect to x means t. Right side C1x, C1 into 1, integration of 1 is x, plus C2 is second integration constant. This we will say as equation number 2. Now let the boundary conditions. Here we will have the boundary condition along the direction of heat transfer, means x direction. So at left surface means x is equal to 0, temperature is T1, and x is equal to your dimension we will take B, that is temperature at the right side face T2. So using boundary condition equation 1, that becomes T1 is equal to C2. So C2 is equal to T1. Now next, using boundary condition 2, we get T2 is equal to C1 into B plus C2. Arranging this equation in this way, and then we will have C1 is equal to this form. So we find C1 and C2, substitute these C1 C2 values in equation 1. We can write T is equal to, this is the value of C1, this is the value of C2. Then this T1 left side, T minus T1 is equal to, then arranging the terms we find this equation, that is equation number 3. This gives temperature distribution in the slab without internal heat generation. Now we know that Fourier's law, that is Q is equal to minus K into A into temperature gradient. Say equation number 4. Now from equation 1 we know that dt by dx is equal to C1, and C1 expression already we know. So putting dt by dx in this 4 equation, that is this term, we get here. Now this minus sign, if we will take outside, then minus sign and this minus sign will get cancelled, and we will find this equation T1 minus T2 by B. Then Writing this equation in this form, Q is equal to Ka upon B into T1 minus T2. This equation gives heat rate flow through the infinite slab without internal heat generation. So this is one-dimensional equation for the slab. That is first application of Laplace equation for slab. Second, we will see about steady state one directional or one dimensional heat flow through hollow cylinder. As we have seen this application in a power plant, that is pipe carrying steam, hollow pipe. So here we will consider this inner radius R1, outer radius R2, inner surface temperature T1, outer surface temperature T2. Heat flow is along the radius direction. Now for hollow cylinder we have this polar coordinate equation reduction form of three-dimensional equation here, that is 1 upon R into T upon dr bracket 1 R into dt by dr is equal to 0. So this 1 upon R will become 0. So d by dr bracket is equal to 0. So here now integrating this equation in order to get value of C1 and C2. So right side 0, this becomes as a C1 integration constant. Once again we derive this by arranging this equation. First of all, equation number 1, that is C1 upon R. Integrating this equation, we find left side integration with respect to R, that is T temperature is equal to C1 into 1 upon R. Integration is natural log of R plus C2. Then we use boundary condition, as already we discussed. At inner side R is equal to R1, temperature is T1, and outer side radius is R2 and temperature is T2. So using boundary condition 1, equation 1, equation 2, this equation, because we want to find C1 and C2. So in this we put value of T as a T1, value of R as a R1, say equation A. Using boundary condition 2, we put T as a T2 and R as a R2. Now this is equation B. Now subtracting equation A and B, we find T1 minus T2, temperature difference is equal to C1 natural log R1 minus C1 natural log R2. Here we can have here C1 as a common term. So we find this C1 form T1 minus T2 by natural log ratio of R1 to R2. Now substituting this value of C1 into equation A, so C1 at the place of C1 we write, so C2 is equal to, first of all we arrange this equation and then we put C1 this bracket. So C2 is equal to T1 minus at the place of C1 this expression we got into ln R1. So here substituting values of C1 and C2 in equation 2, we find T is equal to, at the place of C1 this expression, at the place of C2 this expression. So this T1 term we take on the left side, so it becomes T minus T1. Right side remaining term, this expression T1 minus T2 divided by ln R1 by R2 into ln R minus this expression. Now in this case we find that right side here common we take T1 minus T2 natural log R1 upon R2. So So inside the bracket ln r minus ln r1. So subtraction logarithm means ratio. So ln of r upon r1. Now what we do, we arrange these temperature terms on one side. So T minus T1 divided by this T1 minus T2 comes here at denominator is equal to remaining terms ln r upon r1, this term, divided by this ln upon r1 upon r2. Now this equation we use for the Fourier's law. Fourier's law, here A, area for the cylinder, is 2 pi RL. This is surface area. So from equation 1 already we know dt by dr is equal to C1 upon R, and value of C1 also we know. So we find dt upon dr is equal to this expression. Substituting this equation in 4 means minus k into this area into dt by dx, this equation, into 1 upon r. So cancellation of radius r and this r, remaining terms, and this minus sign and this minus sign get cancelled. So here we find 2 pi kl T1 minus T2 upon ln R2 by R1. Now this equation is heat flow rate through hollow cylinder without internal heat generation. That is second form for the hollow pipe or cylinder. Third case was of spherical shell. In this case, the heat flow direction is along the radius. So here two-dimensional diagram is same as of cylinder. Now here the general differential equation form in for the steady state with no internal heat generation for sphere. Now this 1 upon r square will become 0, and next term we will find this. Next, integrating with respect to r, the above equation, we find r square into dt by dr is equal to C1. Arranging the term, we find equation 1. Once again integrating the equation 1, we find integration of this equation as a temperature T. Right side C1 into 1 upon r square integration is minus 1 upon r. That's why minus sign comes here. Plus C2. Say equation number 2. Now we will use boundary condition. These boundary conditions are same as of hollow cylinder. So directly we will go to the next point. So equation 2 becomes, by using boundary condition 1, T is equal to T1. We write right side here was C1 upon R, at that place R1 we write, minus sign is there already. Then using boundary condition 2, equation 2 becomes T2 is equal to equation this B. Then we subtract equation A and B, means T1 minus T2 left side, and right side this is the equation A and this is equation B. Now in this case, while we are writing this, because of subtraction sign, this plus sign of C2 becomes minus here, and this minus sign of C1 upon R2 becomes plus. So we find here this term C1 as a common term inside the bracket 1 upon R2 minus 1 upon R1. So arranging the equation in the form of C1, we find this equation. Now from equation A, we write this, then we write the equation in the form of C2, because we want to place C1 expression here, which we already got, and then we get C2 is equal to this equation. Then substituting expression of C1 and C2 in equation 2. This is the equation number 2. At the place of C1, this expression with minus sign. At the place of C2, this expression. So simplifying the equation, we find t minus t1 is equal to this minus this term. Now in this case, t1 minus t2 divided by 1 upon r2 minus 1 upon r1, this bracket. So these both brackets are same in both terms. So we can take outside this. So inside the bracket will what come 1 upon r1, this remaining term, minus this remaining 1 upon r. Now the arranging the equation in the form of temperatures, we find this equation. So this gives temperature distribution of a hollow sphere without heat generation. Now as earlier case, Q is equal to Fourier's law. Here area for the sphere is 4 pi r square, that is surface area. So dt by dr is equal to C1 upon r square, that is from equation 1 already we have this. Now again this C1 term we got, that we write here C1 term. So equation is 1 upon r square into this expression. Now substituting this term dt by dr is this term in the equation 4 at this place, and A is equal to area. We can have here equation minus k into this area into this term. Again we take minus sign outside, so that this minus sign and this minus sign get cancelled. Remains 4 pi k into temperature difference divided by 1 upon r1 minus 1 upon r2. So again arranging the terms, finally we find this equation, that is heat flow rate through sphere without internal heat generation. So in this way we obtain Laplace equations for the applications slab, cylinder and sphere. So at the end of this session you can explain steady state heat conduction without heat generation for plain slab, hollow cylinder and hollow sphere. If you like this video, please subscribe and share. Thank you.